Hello everyone. So in this video we are going to learn about interval trees. This is a second case study, or you can say the example of augmenting data structure topic. Already we have discussed what is augmenting of data structures, and in this augmenting data structures we have already discussed uh, how to how to define the order statistics tree, which is again uh, finding a new type using RB tree. So this is another example of augmenting a new data structure. So let's move. So interval trees is again a data structure which is achieved by augmenting red black trees. So here we have a dynamic set of intervals. Means in our normal tree we are having a node. Node basically is having a key value. Now here in interval trees, the node do not corresponding to a single value, but it represent a, a range of values, or it represent a interval. So interval is defining is like that. Uh, T1 comma T2, so it is a kind of range. So I can write like 9 to 32. This represent one interval where this is a lower value and this is the highest value. So intervals are basically very convenient to represent an event that occurs in a particular period of time. You might be interested to find out events that occur during a given period of time. So this kind of data structure will be useful to handle this kind of information. So let's see that how it can be represented and how it can be used. So in the interval trees, actually we are using it to maintain the interval database. So here every node is basically representing an object, and that object is basically defining a range, uh, or you can say a interval that is spread over the time period from T1 to T2. So the T1 represent the is a low end point, and T2 represent the high end point. That means if we have an interval from 2000 to, let's say, 2012, then this is a low end point, and 2012. Now it all depends on the implementation, how we are implementing. We are using a half open interval or a closed interval. So if I say normally we use it as a closed interval, means this value is inclusive, means the lower value and the higher value is inclusive within the interval. So in our example also, we are representing our interval tree as a closed interval where both the values, the low value and high value, is actually included in the range. Now we have three possibilities. So we have A, B, and C. So with this is case A, B, and C. So the first is that we are giving a two set of intervals, and the two intervals are actually overlapping. So you can say that this I is contained within the I dash, or I dash is contained within the I, or you can find that I dash is actually having some overlapping with I. So if you look to these scenarios, this is something that I is having value 20 to 50, and I dash is having, let's say, 10 to 70. So you can say that I is actually included within the I dash. Similarly, this is the reverse scenario. If we look to this, where I and I dash are representing like this, so you can say that I may be representing to an interval, let's say 20 to 30, and I dash may be representing from 5 to 25. So you can see here that the high end of the I dash is actually more than the low end of the I. And also the low end of the I is more than the I dash. So this is this kind of scenario where there is an overlapping is occurring. That means from value 20 to 25 is actually overlapping in these two intervals. If you look at this, this is a scenario where the high of the I, means we have two intervals I and I dash, and the highest value of the I is less than the lowest value of I dash. Or you can say in the reverse way, the highest value of I dash is less than the lower value of I. So these are not overlapping, and this is an overlapping case. So in this interval tree, we are performing some operations. So we'll see that what operations can be included here. And because we are doing augmentation in an existing data structure. So here the data structure that we have used for augmenting is RB tree. So that means if we add these operations and if we add any of the field in the existing data structure, then it should not violate the basic operations of RB tree. This should be also maintained. That we will also check and verify that this augmentation is accepted because it does not violate any of the augmenting rules properties. So So interval tree, here we are going to, this is arbitrary. So it has the default fields are always there. Like it has a link for the left and right. It has a field for the coloring. It has a field for a node. This is already defined in the arbitrary. So you may use these default fields for your new definition, or you can just leave as it is, and you can add from your side some new fields. So here we are going to add one field intx, which basically represent an interval. So x represent an interval here. So when I say intx, this is basically an interval which has a high value and a low value. So if you want to insert uh, any interval in the interval tree, then we can say t is the tree that we are using and x is the interval that we want to insert. Okay. Similarly, delete basically in this tree we are deleting this interval x. So the procedure remains the same. It is a binary search tree. So the intervals are actually sorted uh, in a in some order. And if we want to search for any interval, then we need to start from the root node, means from the root interval, and then we proceed as per the given condition. If the interval is less than the root interval, then we move towards the left subtree. Otherwise, we go to the right subtree. Similarly, for the insertion, deletion, and searching will be same as we have discussed in the normal binary search tree operations. So these three operations are to be used, and then we have to see that when we perform these operations, it does not violate its basic structure. That means it does not violate the running time of all these operations. So in arbitrary, since it is balanced, so the running time is log n. Okay. So here you can see that some intervals are given to us, and based on the intervals, we have uh, constructed our this interval tree. So you can see that some intervals are overlapping. These are called overlapping interval. This is not overlapping. These are also overlapping. These are also overlapping. So these are said to be overlapping interval, and this is a interval tree. So how this interval tree has been created? Let us understand. So here the basis for inserting the node is depending on the low value of any interval, means 16. In this case 16 and 21 we have, so 16 will be acting as a decision parameter to decide that the new interval to be inserted as a left subtree or a right subtree. Now here we have also used one field called max. So max is basically here representing the maximum value that can be existing in a given tree. So if you look at this, this is one interval tree. So this max is 30. That means that this particular tree is having maximum value 30. So if you are having any interval, let's say 50 and 80, and when you go to the root node, you can simply look the max value, and we can find out that this interval does not belong to the part of this particular kind of interval tree, because the maximum value that exists here is 30. So this this way we can use this max value here. So let us see that how this is constructed. So you can look here. Okay, let's see that how this tree is constructed. So as we know that whenever we insert anything, it always go to the leaf. So that means when we start constructing our tree, then 1621 is the first thing to be inserted as an interval. So we insert 1621 as a node, and then every node will also contain the maximum. So at this point of time, the maximum value that this tree represents is 21. So 21 is here. Then let's say the next interval you insert is 8, 9. So you inserted 8, 9. So what is the criteria? So you will find that the low value, that is 8 here. 8 is less than this low value of 16, then that means it should go to left side. So you will go to left and you will add a node as an that represent interval. So 8, 9. Now also you have to check before you insert this value, you will check that what is the what is the high range here, and every time we have to update the max value. So for updating the max value, what we will do, we will see that uh, here the maximum value is 9. So we will write 9 here. If you find that before you insert this value, and if you find that this value is more than 21, then this value would have changed. For example, let's say this is 92. So definitely it goes to the left side because this is less than the lower value of this interval. So it should come left. But since this is 92 and this is 21, so you need to make it 92 here. This is what is required, and also we are doing 92 here, but this is not in our case, so we will simply do like this, that this is 21, this is our tree, then we go left, this is 8, this is 9, and this is 9. Then let's say next we are inserting 25 30. So 25 30, so 25 is more than 16, so we are going to make this as a right interval, so 25 30. But we have noticed that this the right value means the extreme value is more than this value, so we are going to update to 30, and we are writing 30 here. So let us insert one more value. Let's say we are inserting 1719. So 17, so we start from the root node. 17 is more than 16, so we'll go here. Then 25, 17 is less than 25, so we go here. That means this interval to be added here is 17 19. At the same time, we will also see that this is 19 and this is 30, so this is not going to change. If this value is more than this, then we are going to update this. Otherwise, we will leave as it is. And for this, the maximum value comes out to be 19. Let us insert one more value. Let's say 1920. Okay, so we start from here. So 19 is more than 16, 19 is less than 25, 19 is more than this. So you are going to insert here 1920. And then you have to write the max value also. So here it comes 20, but because the maximum value of this is 20, which is more than this, so we are going to update this as well. So likewise, you can also insert other nodes, and I believe you understood that how the nodes have been inserted and how this max value has been maintained. So let us see that whatever we have discussed so far, is it a feasible augmentation or not? Because in order to make any augmentation feasible, we need to verify all these four things. Four steps are there. So we will see. The very first thing is we need to identify which data structure we are going to use. So we have identified red black tree to be augmented. In this red black tree, we are going to add one field intx, which basically represent the range or the interval. And the key value means the decision on which we are going to process, means when we are doing insertion, we have to process, we have to, when we are doing deletion, we have to process. So during all these operations, we need some key value. So here the key value is defined as low of integer x, means on the basis of the lower value we are doing our decisions. So for example, when we are inserting any node, whenever we are inserting any interval, then in order to decide that which where to forward, you need to make the interval at the right subtree or the left subtree. It is decided on the lower value uh, of the root value. So for example, this is interval 20 50. Let me write it again. 20 50 is given here, 50 is here, and we are going to insert any interval. Let's say 12 17. Then we will check this lower value of this and the lower value of this, and this is less than this, so we have to go left side. Okay, and also when we are making another traversal, then they are sorted on the basis of their this low intx. Then additional information. Also, we are going to, you know, use one value max x. Max x is basically defining the maximum value of any interval endpoint that we have discussed. So it is the maximum value of all right endpoints in the subtree rotated at x. This already we have discussed. Then how this max is to be maintained? So max is basically maintained by looking to the in the high of this interval and the left of this interval and the right of this interval. So you will find that if you have any tree here, so among all the max, so let's say this max is 20 at this any point. This is 20 and this is let's say 20 and this is 12. So among three, whichever is the maximum value, that is defined in max. So max basically take the maximum among all these three. Now we have seen that to find out the max, it is a kind of a simple comparing the three values, which is a constant time effort. So to maintain this max, it takes 0 1 time, and even if we are doing any rotation during the insertion deletion, so rotation will be done, in maximum, we are doing maximum 1 or 2 rotations, and as a whole, it will take log n time. So here also, if we want to maintain this max f, if we want to maintain the max x, then also being a constant effort, it will not make any impact on the insertion deletion, and it will still be running in the log n time. Then we are developing a new operation called interval search ti. So here we are going to pass our tree and we are going to search any interval I in the given tree. So what it does, it basically tries to identify that interval. So we start from the root node, and then if the root itself is the interval that we are searching for, we are done. Otherwise, we have to move left or right. And there's a scenario that you might be searching an interval which is not a part of the tree. So if you are end up with keep on going in one direction, and if you reach to the leaf node, and also you are not able to find your interval, then you will say that your interval is not existing in the given interval tree. So let's look to the algorithm. Okay, so interval search ti. So we are searching this interval I, and we need to traverse our tree. So we will make a temporary pointer, you can say, for traversing. So we'll say that x is a temporary pointer that we use to move. So x is actually representing the root of the tree. So if x is not nil, means the tree exists. Okay, if x is not nil, the tree exists, and I does not overlap with int x, means the tree exists and there the root exists, and the I which we are searching is not found at the root node. Then we have to proceed to the to the left or right. Otherwise, we are done. So if the tree has a left child, and also the maximum of the left x is more than the low of I, means we are having this, let's say, the scenario. This is the node and this is the left and this is right, and let's say you are searching for uh, 10 20. Okay, and the max value written here is 15. So if the max of the left tree is more than the low of the interval that you are searching, then you need to move to the left. This is uh, what is said here. So you move to the left means, now earlier this is your x. Now when you move to the next part, this becomes your x. If this condition is not satisfied, means this max value is not more than the low of the interval which you are searching, then you move to right, and then right becomes your x. And we keep on searching until we find that our x becomes nil. That means the element means the interval that we are searching is not existing. So so we have seen that actually the operation that we are performing is requiring a constant cost, because we are doing certain comparisons. So in a BST, the cost of the operation is log n. So still, uh, this is a constant operation and it does not make any change on the default operation cost of the RB tree. So the entire such procedure will remain the log n. So that means we did we add some variables here, we add some procedures here in our default RB tree, but the resultant tree itself uh, performing all the default behavior. does not deviate from its default behavior means the running time of insert and deletion is not going to change. So we have uh, verified and make sure that all the properties which are required for augmenting data structure is being satisfied. Now understand this with an example. Here we want to search the interval 22, 22, 24. So the lower limit is 22. So we have to focus on this 22 value. Now here, this is our root node. So now first we check, is it overlapping or not? So we can find out that this interval does not overlap this interval because the maximum value of this is actually less than the lower value of this. That means this is definitely not overlapping. They are not coming in the boundaries of any of the two intervals. So now we have to decide where to move. So what we do, we have an algorithm here. So we look to the left. In the left subtree, we look to this value. Now this value 23 is more than 22. So whenever we find that this max of left x is more than low of I, then we go to left. So that means we are moving here. So x will be here. So also the same thing is mentioned here. We start with this and then this is the root node and then we find this is 23. 23 is more than 22. So we go to the left child of the root and we are here. Again, we need to see that is it overlapping with the requirement. So we are looking for 22, 22, 24. This is 8, 9. So the high value means the maximum value of this is less than the low value of this. That means both the intervals are not overlapping. So again, we have to see the left of this. This is 10. So here we find that this max of this is not more than the lower of this. So in this case, this condition does not match and we will go to right side. That means now we'll come here and this becomes x. So here you can see here that we will 8, 9 we are checking and then we find this is not overlapping and we find the left of x is 10 which is lower than this. So we go to the right child. So we are here. So here you can see that the lower of this is actually less than the higher of this. That means this comes within this higher. At the same time, you have to also check that this lower of this particular interval is also less than the lower that we are searching. That definitely means if this is the case 15, 23 and then this is 22, 24, that means this part is going to overlap and we are done with the search because overlap says that either they are contained within to any of to each other or they are just have a kind of overlapping to some of the part. It is considered as overlap. So we are done with our search and this is returned as an answer. So in this case we have find the element. There may be a case you are searching in an interval and the interval will not find out and you are end up with the answer that interval does not exist in the given interval tree. So let us take one more example. We are searching for interval. Interval is 11, 14. Okay, now let us check that 11, 14. So you will find that the high of this is less than the low of this. That means they are not going to overlap. So the root is not the interval that we are searching. So we look to the left side. This is 23 and we find this 11. So 23 is more than 11. That means we have to go to left side. So we will go here. Now again we'll check, is it overlapping? Again, this range and this range has no overlap. So we need to decide where to move. So now we are here done. Then with 10, this is 10. Now this 10 is less than 11, 4. So we have decided to move to the right, 15, 23. And all the steps you can also read from here. So I think you can just read this algorithm and the step that we are doing is mentioned here. And I am showing you here how it is going to work. So now this is again 11, 14 and 15, 23. They are not overlapping interval. So now you will be searching for left. So if x is not equals to nil, then only you are going to compare with the max element. If x is nil, then definitely you are going to the right part. But right part is also nil. That means there is no more node exist, there is no more interval exist, and you are end up with the decision that this interval does not exist in the given interval tree. So this is how the interval tree is actually work. And I believe that you understood that this is interval tree and this is an augmenting of RB tree data structures. So we have seen that how the fields to be added into the RB tree data structures, how the operations are to be added, and then how we have verified this. Already we have discussed in detail in our previous lecture. So thank you very much. This is all for this lecture.